Hi, this is the pre-lab video for your Lenses and Geometric Optics lab. Part of it will be done with equipment, and we want to let you guys know what is and is not acceptable, but you probably figured out yourself. So the theory behind this is mostly the thin lens equation, which mostly comes in this format. Inverse DO plus inverse DI is inverse F. So what do those mean? F is the focus of the lens, which is dictated by the stuff that it's made up out of, and its geometry. So you can kind of think about that as fixed in the factory. And DO and DI are the image and object distance. So on image, this would be, and you'll draw ray diagrams at length in this class. So the object distance would be this, the distance from the object to the lens. And in this case, I didn't draw the rays for the ray diagram, but this object is making a real image. So the light rays are actually coming off of the object, and they're actually converging there to form a real image. This would be DI, the image distance. And for a lens, this would be, so for anything, this is always positive. For a real image, this is positive. The rays actually converge on the far side of the lens. So here's a real image. The other hallmark of a real image is that it's inverted. So this is upright just because that's how we drew it, and this is inverted. So the other option is that you have, you can make a virtual image. So in this case, this is still DO, this is still DI. All of these distances are measured from the lens, including the focal length. But this would actually be negative. So in this case, what I would have is DI is negative. It's on the same side as the lens. So this is a virtual image. I know it for two reasons. One is that it's on the same side of the lens as the object. It's not going to make a lot of sense to me when I'm actually looking at things. All images are actually in my brain, not on one or another side of the lens. The real smoking gun that this is a virtual image is that it's upright, just like the object is. So these are the tracebacks of rays that seem to have come from here, but didn't actually converge. So we'll show that with an actual setup. So here's a lens, and here's an object. You can actually see it when we swivel the camera around. It actually has a nice little arrow pointing upwards on it. This is DO, this is DI, where an in-focus image is projected. And because there's an in-focus image projected here, light rays are actually converging there. This is definitely a real image. DI, DO, real image, and we'll show you in a second that this is inverted.
You want that?
Sure.
I'm gonna give you that. Okay. Here's the awkward part.
I mean, like all of physics is the awkward part. Okay. Cool. So here, you give it a chance to adjust. See how this is an upright arrow. So this is the object, the actual light box. And then there, the image itself is inverted. So both of the things that I could ask definitely tell me that this is a real image. One, it's actually projecting on a screen, and two is that it's inverted. So for a virtual image, you wouldn't be able to project it onto a screen, and you would see that this thing flips. So now I'm actually, hopefully this adjusts well enough.
So we're at real image right now. Let's scoot this back a little bit.
Yep, so this is...
Now we're into the virtual image regime.
And how do I know it's a virtual image? Well, I'm looking through the lens, and if I kind of scoot down, I can see that the arrow is upright. So there's the image arrow, there's the virtual image arrow, and they're both upright. And as it scoots back, you can actually see everything go crazy as it flips from real to virtual.
Or backwards, going from virtual to real.
Virtual to real, sorry. Yeah. So upright, and then craziness, and then see how the bulby part, the circle is on the top now, whereas on the original image the circle is at the bottom. So virtual images, kind of cool to draw, a little bit annoying to deal with. So the question is, when you guys who don't have access to really nice precisely milled lenses, and you're not allowed to disable your siblings' glasses to do this, or if you do, don't tell us about it. what can you possibly use for lenses? And it turns out that a variety of
You can use a nice 2011 Italian Pinot Grigio. That would work fantastic. Only make sure that if you do get a wine, it's only the highest quality, high-end stuff. You don't want to skimp on quality here. You can also use just an Nalgene bottle. If you've got cylinder or something, you just regular old glass that you've got that you might have. For drinking water, that'd be fine. Anything that's somewhat transparent will work just fine. Problem is, you want to make sure it's got straight sides. If you've got something that's got curved sides like this, that's going to have a varying focal length, because focal length is a function of the geometry of it. You calculate it from twice the radius of your lens. So if you've got something that's curved, that calculation of twice the radius is different for here than it is for here. You've got a different focal length for each of these points. So anything that's tapered or got structure to it, don't use that. That's bad. You want something that's got nice flat parallel sides on here. That'll work really well as a lens. And if you want to see this thing in action, we can do just one real quick action shot. I'll use my high-tech light source here. Get these out of the way. And you can kind of see this is where we are. So I'm out of focus. Now I'm focused right here. I've got a nice converged point where my image is. Kind of focusing down to a thin line. Then I go beyond it and it gets blurry again. So that's going to be the point where you want to make that measurement. And again, DO is from your light source to center of your lens, because we're pretending it's a thin lens, because thin lens equation. Yeah, so we'll just apologize to the powers that be and still measure to the very center of our lens. And then DI, again, middle of the lens to the image out here. And that should be that.
Yeah, but Chris, that scruffy guy was semi-coherently rambling about being able to measure if something was upright or inverted.
Oh,
Could I do that with my cell phone?
You could totally do that. So let's get an image on here again. So what I'm going to do is I'm going to bring my finger in from one side of the screen. I'm going to bring it in from my side, closer to me, and push it out. And look at that. So you see which side of the screen starts getting dark. That shows you which side is which side is up on the image. If I'm on the right side pointing my finger across and the left side is getting darker, then I've got an inverted image. If it's the other way, if I'm bringing my finger in on the same side as is getting dark, then it's an upright image. That is an excellent question, class.
Yeah, so think about not just up-down inverted, but left-right inverted too. So we didn't make a big point of that on the light box, but when it's flipped up-down, it's also flipped left-right, and you can totally investigate that by blotting out part of your light source. All right, good luck. Ransack the wine cabinet.